Welcome to the National Weather Center. This is the home for the Center for Autonomous Sensing and Sampling, as well as several other government and academic agencies centered around the field of meteorology. Today we're going out in the field, which is where we spend a lot of our time, and we're going to check out a new piece of equipment that's going to make that job a lot easier for us.
The University of Oklahoma and the Center for Autonomous Sensing and Sampling is home to the CopterSonde, a well-characterized and highly reliable UAV-based thermodynamic and kinematic vertical profiling system. In our normal mode of operation, we use a ground station comprised of tents, tables, chairs, chargers, computers, and antennas. We carry that gear in a trailer, and it takes about 20 minutes to set up or tear down. Being as mobile as possible allows us to make measurements while moving with mesoscale features. We saw that setting up and tearing down was limiting our ability to be mobile, so we redesigned our whole ground station. Introducing the CASS truck, a UAV ground support vehicle designed for nomadic and rapid UAV deployment. The front seat operator has an internet-connected computer, and they handle navigation, weather monitoring, and checklists. The rear seat operator has a fully connected UAV ground station, including telemetry, RTK GPS, and battery charging. The drone mount and charging are built together in a swappable module that allows us to support future versions. Below that are the electronics for the truck. The antennas are conveniently mounted on a rack, keeping the bed space open. And powered by 2 alternators and 2 batteries, the truck is equipped with a 2200 watt pure sine wave inverter. This provides plenty of power for missions and repairs in the field. We are confident in this system, and we believe it will unlock a new paradigm in OU's mobile UAV weather sampling.
Welcome to Max Westheimer Airport. My name is Francesca Lappin, and I'm a graduate student for meteorology here with CASS. Right now, we're at the University of Oklahoma's own airport where students learn to become pilots. We will be conducting the first ever UAS flight at an active airport today to collect weather data. This data will be used to improve air traffic management. So let's go check it out.
So what I'm holding here is the CopterSonde, and we're here at the airport, Westheimer. And today we're gonna test the CopterSonde. We're gonna actually demo some flights. We're gonna show that we are capable of flying the CopterSonde near the airport. The CopterSonde is equipped with some really cool instruments to watch around for planes. We can actually detect and avoid. For now, we're looking at it, but in the future we're gonna have something like an autonomous avoidance for it. But we're working with the people at the airport to have it working close to the airport and monitor the weather close to it. Basically added an ADS-B receiver to the drone, to the CopterSonde. So what it does, it listens to any ADS-B transponder that is flying around from an aircraft, and that is sent down to the ground station, and the ground station then displays the planes on the map. So we can exactly see where they are around the copter, and we can take decisions of avoidance or continue the mission, you know?
Westheimer Tower, November 936, Uniform Alpha, request vertical profile. Roger, November 963, Uniform Alpha, proceed as requested.
It's been an extremely successful day here at the airport, and while Tony continues to collect more data, let's take a look at some of the motivations behind why we designed the CopterSonde, as well as some of the field campaigns that CASS has been a part of in recent time.
Auto mode and take off.
There's such a data gap that exists that we need to solve, and drones are the best way to do that. We kind of hit a wall with the commercially available drones, and that's what prompted us to build our own. And we found out that building our own, we could wind up getting better drones than we could ever buy.
We're taking a lot of commercially available sensors and integrating them into a payload that will enable us to measure exactly what we're looking to study.
We build the whole thing from the ground up. And by doing that, we can get data that no one else can get.
So CASS gave me the opportunity to build my own drones, experiment with them, create something really new from scratch. So that's why I'm here. It's something I always wanted to do, fly drones, develop drones, optimize drones for specific applications such as the meteorology research.
Our engineers are brilliant and have been developing platforms from scratch, integrating the sensors themselves. A lot of previous studies have used tower data, have used LiDAR and ARRI and remote sensing data. Not many studies have ever used all of those combined with the UAVs.
What we do, both in the lab and in the field, requires a really diverse team. We have people from nearly every engineering discipline and several science disciplines working together to better understand the world that we live in.
We have a very interesting opportunity now to take information we're getting from simulations and supercomputers of these thunderstorms and use that information to guide field experiments with the UAS we have here in CASS. One of the biggest questions we still have about thunderstorms is why do some thunderstorms produce tornadoes and others don't? Why is it that you might have one storm 50 miles to the north that produces a tornado while one storm 50 miles to the south does nothing? And we think it's things on the scale of the storm, so things going on right around the storm that make the big difference between whether or not they're going to produce a tornado. We have a fairly good understanding of the large scale quantities that make the environment productive for tornadoes, but that doesn't guarantee that every storm is going to produce one. Earlier in this video, we mentioned the CASS truck and how that's going to revolutionize our ability to conduct mobile experiments with drones. And by using the drones, we can access regions of storms that weren't necessarily accessible with conventional methods, like ground-based sensing, radars, weather balloons, etc. And so we're hoping that these drones will allow us to get into storms and get information from regions not previously possible, and that'll help improve forecasts and ultimately save lives down the road.
Came together in the San Luis Valley in Colorado to examine how we can use unmanned aerial systems or drones to sample the atmosphere. We're here to really understand there's three primary science questions. One is what actually drives the initiation of convection? What is it that causes storms to fire in a particular area?
We also studied drainage flows, and that's how air gets cooled and then flows down a valley.
And the third one was just a traditional morning profile, where we were just examining how we would transition from a nighttime environment to a daytime environment.
It's about 2 p.m. We're in the northern part of the San Luis Valley, and there were thunderstorms going up on top of the mountains earlier this afternoon. But now if you look off to our northeast, we see that the clouds are starting to make their way down the valley, down the sides of the mountains as they're riding on top of that cold air outflow from the previous storms. Eventually, these clouds will make it all the way into the valley and will more than likely grow into larger scale thunderstorms.
So we've been developing our own custom-made drones that we're flying today. These are quadrotor copters that are equipped with pressure, temperature, humidity sensors.
So with the drones, we can get how all that forms with really great detail that we have no other way to get.
Gus, we need the RTL.
Getting profiles of these types of measurements is what organizations like NOAA, and the National Academy of Sciences, National Science Foundation are really pushing to get more information on.
Long term, we're going to learn a lot more about how these complex flows interact with the terrain, with all the different thunderstorms and the larger scale weather systems, how it interacts in the mountains, at higher elevations, at different times of the day, throughout different seasons. And ultimately, this will lead to better forecasts for you and me and everyone else who needs a good weather forecast.
Okay, now let's check out the data.
Python is a common programming language used in meteorology, and it's commonly used here at CASS for post-processing and data analysis. So these are some examples from today's flight, and you'll notice that in this plot we have a green line and a red line. The green line shows dew point temperature, which is a gauge of how much moisture is in the air, and the red line shows the air temperature. And if you scroll down through these, you'll notice that at the surface we get warmer as the day goes on. So as you get further into the afternoon, sun gets higher in the sky, you heat up. And you'll also notice that the dew point temperature gets further away from the air temperature as the day goes on, meaning that it's gotten more dry at the surface as well. And if we run this second line here, this plot's what's known as a time height plot. And on the x-axis, you'll see what's known as UTC time, which is Universal Coordinated Time. And Universal Coordinated Time is a time that's used throughout the world so that everybody can be consistent. In Norman, Oklahoma, this time of year during daylight savings time, 18 UTC would be 1 o'clock. And you'll notice on this plot that in the morning it's quite a bit cooler, and as you move throughout the day, again, you get a lot more heating at the surface, and so you see that it warms up really throughout the lowest 1 kilometer in this plot. Time height plots like these give us an understanding of the stability in the lower part of the atmosphere. The more unstable the lower atmosphere is, the more likely you are to get things like thunderstorms. It also has a large impact on turbulence. The more unstable the lower part of the atmosphere is, the more turbulent it's going to be, which has a massive impact on the operation of small airports like the one we did measurements at today. Everyone here at CASS would like to thank you for joining us here at the 2020 National Weather Festival. Be sure to check out all the other information the festival has to offer, and we hope to see you again next year.